This is our last review before the final exam. We'll try to make it quick and hopefully get you guys out of here with some new knowledge or reviewed knowledge of functions. Let's start with the first 6 problems. So the first 6 problems are all different forms of compositions. Remember when we did this function machine activity where you had to plug a number into one of them and then take that answer and plug it into a different one to try and figure out which one had the correct combination. So that's what compositions are. We're taking either numbers or expressions and plugging them into functions and then possibly even plugging them into multiple functions. So the one that we're going to do together is number 3. When we see number 3, this, if I'm going to read this, first of all, we have a function defined for g of a, we have a function defined for h of a. This expression right here means to perform the operation of a composition where we have g of h of a, and essentially what that means is we're going to take the function h of a and we are going to substitute it in to g and then evaluate, or plug it into g and then evaluate. So this is the function h, and this is the function g, and everywhere I see an a, everywhere I see a variable in the function g, I am going to substitute in this function h of a. So I'm going to substitute in a squared minus 4. So instead of writing g of a, I'm going to write g of blank, because I know I'm going to substitute something in for the variable a in this composition. Instead of writing 3a, I'm going to write 3 blank, because I know I'm going to substitute something in for that a. I'm going to replace the a with a expression. And then this plus 2 doesn't have any variables in it, so I can just write plus 2 right here. Now I'm going to take, I'll do it in red, I'm going to take this expression for h of a and I'm going to substitute it into the function g everywhere I see a variable. So I'm going to take a squared minus 4 and I'm going to plug it into the function a squared minus 4, a squared minus 4. Now over here on the left hand side, this is just function notation. All that this is saying is that we are taking the expression a squared minus 4 and substituting it into the function g. You're not actually supposed to simplify anything. You don't do anything with that side. That's just what we're actually doing over here on this right hand side. So over here we have 3 times a squared minus 4 plus 2. Order of operations says to distribute the 3 first. When I do that, I get 3a squared minus 12 plus 2, and then I have some like terms that I can combine. So 3a squared minus 12 plus 2 would be 3a squared minus 10. And that's the final answer for number 3. I want you guys to try number 2. So go ahead and take a minute, and I'm going to put up some answer choices over here on the right-hand side, and I want you guys to answer number 2. All right. So for number 2, hopefully you guys chose the right answer. We're taking this value of negative 2a and we're substituting it into the function g everywhere we see an a. So g of negative 2a would be equal to, and again, I'm not multiplying it times this a squared, I'm substituting it into that value for a squared. So it's going to be blank squared plus 2 times blank. And inside of that blank, I'm going to be writing this value of negative 2a. I'm substituting this into the function g everywhere there was an a. So if I plug it in, I get negative 2a squared, and then plus 2 times negative 2a. Order of operations says to square this first. Negative 2a squared, which is negative 2a times negative 2a, is positive 4a squared. And then over here, positive 2 times negative 2 would be negative 4a. So that's the correct answer, 4a squared minus 4a. All right, numbers 5 and 6 we're not going to do together, but those ones are a little bit more challenging. This one essentially is to take this value t plus 1 and plug it into g, substitute it into g, get an expression for that, and then take that entire expression and plug it into h. For number 6, we're taking that expression for 2t and substituting it in for h. When you get an answer for that, plug that whole expression into g. So these ones are a little bit extra challenging, but go ahead and give them your best shot. All right, the next ones we're going to look at are from the inverse section, so we're going to talk about numbers 7 through 10. Remember, for this picture from inverses, if you are giving a gift, you put a ring into a box, you wrap the box, you put a bow on it, and you give it to somebody. For someone to undo that, we are undoing the things that you did in the opposite order. So somebody would receive your gift, take the bow off, unwrap it, take the lid off, and then take the ring out of the box. So that's essentially what inverses are. We're going to look at number 8 together. So if we look at number 8, the very first step for inverses is always to replace the name of the function with y. So instead of writing f of x, I'm going to write y. The next step is to switch the x and the y. So I'm going to just rewrite this as x equals negative 10 plus 7y, over 5. And then the last step is to solve for y. So we are trying to get y all by itself. One of the things that's important for you to be able to do is to identify which mathematical operations are happening to it and what is happening in what order. So if you look at the y, the first thing that's happening to that y is that we are being multiplied by 7. So 7 times y, I'm just going to make a little note over here in red, that the first thing that's happening is that we are multiplying by 7. So we have this quantity 7y. What's the next thing that's happening to it? Well, it's kind of in a weird order, but technically the next thing that's happening to it is that we are subtracting 10. I know that the 10 is before that 7y, but if you had moved it afterwards, it would be 7y minus 10. So that's minus 10. Subtract 10. So we have this quantity of negative 10 plus 7y, and the last thing that's happening to it is that we are dividing by 5. Just like in the gift-giving example, we first multiplied by 7, then subtracted 10, then divided by 5. So in order to perform the inverses, we're going to undo those things in the opposite order. So instead of dividing by 5, the first thing I want to do is multiply by 5 on both sides. That's going to undo the division. That's the inverse of division. So if I multiply by 5 on the right, multiply by 5 on the left, and simplify, there we go. And simplify, I get 5x equals, the 5 on the right multiplying and dividing divides out to be 1. So it equals negative 10 plus 7y. Great, I undid that. The next thing I want to undo is this subtracting 10, so I'm going to add 10 to both sides. Plus 10 on the right, plus 10 on the left. Over here on the right-hand side, negative 10 and positive 10 add to 0. Those are additive inverses, so we're left with 7y. On the left-hand side, we have 5x plus 10. Those are not like terms, so the way we write this is just to write them right next to each other. And last but not least, to undo the multiplication of 7, we would divide by 7. Divide by 7 on the right, divide by 7 on the left. On the right-hand side, 7 divided by 7 is 1, so we're left with y. And this is actually the inverse function, so I'm just going to put y inverse, or in fact, the name of the function, which is f of x, so f inverse of x, is equal to, on the left-hand side, you don't have to simplify this. You can leave it as 5x plus 10 over 7, and that's our final answer. I want you to try number 7. So go ahead and look at number 7, try to find the inverse, and select the correct answer choice. All right, for number 7, step 1 is to replace the name of the function with y. So we have y equals 3x plus 8. Step 2 is to switch the x and the y. X equals 3y plus 8. Step 3 is to isolate y. So the first thing that's happening is that we're multiplying by 3, and then we're adding 8. So the first thing I'm going to undo is subtracting the 8. Minus 8 from the right, minus 8 from the left. These are not like terms. X minus 8 equals 3y, because those add to 0. And then the last thing I'm going to undo is the multiplication of 3, and I'm going to undo that by dividing by 3. So divided by 3 on the right-hand side, divided by 3 on the left. Therefore, on the right-hand side, since my 3's divide out to be 1, I'm just left with that y. So that's going to be g inverse of x, now that we have an inverse function, equals, and again, don't worry about simplifying, x minus 8 over 3. Final answer. Hopefully that's the one you chose. We're going to go ahead and look at some graphing problems now. So the one we're going to do together is number 11, and then you guys can look at number 12 on your own. So for number 11, first thing we want to help ourselves do is identify which function this is. So this is a quadratic function. The negative in the front indicates that we have a reflection over the x-axis. The 1/2 is a compression. This is going to be a compression of 1/2. This 2 inside the parentheses is going to indicate a shift to the right. -2 shifts to the right 2 units. And this +1 on the outside of the parentheses is a shift up 1 unit. So the way that I do it with you guys, hopefully all the other IM3 teachers do it similarly. We look at what I call the ghost points. So if you think about a quadratic expression, a squared function, y equals x squared, if we have these x and y points, we start with these 3 points, -1, 1, 0, 0, and 1, 1. These are the 3 points that if you had, and I don't want to necessarily see them, but if you had plot them and connected them, that's the parent equation, y equals x squared. So the way that we do this in our class is we take these points and we multiply them by the a value. So the a value is -1/2. If I multiply these 3 y values by -1/2, 1 times -1/2 is -1/2, 0 times -1/2 stays at 0, and 1 times -1/2 is -1/2. Now, I tell my students I want you guys to plot these, we call them ghost points, because I want them to just be little points that are not actually there. They're just kind of little invisible points. So here's the one at -1, -1/2. Here's the one at 0, 0. And here's the one at 1, -1/2. Now, the only reason I like to put them on the graph is because it helps me to have a nice idea of what the shape of the graph would look like. I don't want you to actually connect these points. That's not where the graph is supposed to be. That's just what the shape of the function looks like. We still have to transform it horizontally and vertically. So let's go ahead and undo my sketch of it. Remember that this 2 meant that we're shifting to the right 2 units, and this 1 meant that we were shifting up 1 unit. So I'm going to take all 3 of these points, and I'm going to shift them to the right 2 units and up 1 unit. So for this first one, right 2, 1, 2, up 1. All right, that's where that new point is. So I'm just going to cross it off. You don't necessarily need to cross it off, but that's where it moved. It was here, it moved right 2 and up 1. This one, at 0, 0, I'm going to move it to the right 2 and up 1. So go ahead and put your point in here at 2, 1. And this one, I'm going to move it to the right 2 and up 1. Go ahead and put your point right here at 3, 1/2. And now, this is a final answer for what our graph should look like. Connect it with the best representation of a parabola that you can. This has been shifted 2 units to the right, 1 unit up, reflected over the x-axis, and compressed by 1/2. Now, for number 12, I want you guys to tell me where the locator point would be. So using the fact that this is your parent function and using all these transformations that are happening, I want you to tell me where your locator point would be. So that one that was at 0, 0, where is it now? So go ahead and answer that question for number 12. All right, so the locator point is actually at -1, -4. So -1, -4. That came from this. The +1 shifted to the left 1 unit, so that's why it's at -1. And the -4 on the outside shifted down 4 units, that's why it's at -4. This negative in the front doesn't have anything to do with where the locator point moved. It just has to do with the shape of the graph. So if typically the cubic function comes up like this, but because it's negative, it's just going to be upside down. So you're going to draw yours something like that when you actually go ahead and sketch it out. All right, numbers 12 through 16 are all pretty similar, so I will let you guys go ahead and work on those. The next one we're going to look at together is 17. Number 17 says to write the equation in vertex or transformational form. Now remember that vertex form is the same general equation with the a's, the h's, and the k's. The only thing that's different is which function we're looking at. So here we have a parabola, here we have a cubic function, cube root function, here we have an absolute value function, and here we have a cubic function. So your parent equation will change, but the a, h, and k are all very similar to each other. For number 17, our locator point is right here. All right, that helps us with our h and our k. So if we check out our horizontal shift, it was shifted 1 unit to the right, that means h is 1. And it was shifted 3 units up, that means k is 3. For our a value, if you look closely at our locator point and then you look at the next one over, from the locator point it went over 1 unit, and then notice that it only went up 1/2 of a unit. That means our a value is 1/2. So since this is a parabola, we have our a, h, and k. I can go ahead and write my equation. It would be y equals a, which is 1/2, times x minus h squared, since it's a parabola, plus k, so plus 3. And that's the final answer for number 17. I would like you to try number 19, and then go ahead and choose the answer that you believe is correct. All right, this is an absolute value function that has been vertically compressed, shifted 10 units to the right, and reflected over the x-axis. Now, the only thing that should be different, possibly for different people's answers, is the compression. It doesn't specify what the compression should be. And so if you look at the answer choices, the correct one ends up being y equals negative 1/3 times the absolute value of x minus 10. The reason for that, the reflection over the x-axis. Right here it says it was reflected over the x-axis. That's why there's a negative. The vertical compression, any number that's less than 1 but greater than 0 is a vertical compression. So 1/3, 1/2, 0.3, those are all vertical compressions. The 10 units to the right, shifted 10 units to the right. Horizontal shifts are always inside either the parentheses or the absolute values or the radicals. So that's why the 10 is inside. And shifting to the right is a negative 10 because of the x minus h, that would move it to the right. So this is the answer that you should have chosen as the correct answer. Numbers 21, 22, and 23 are all kind of gimmies. So I'm not going to do them for you. I will just ask you guys the questions about them. I'll just kind of give you a little hint before I ask you the question. For number 21, you guys can do on your own, describing the parent functions, what's the shift left, what's the shift right, etc., etc. For number 22, it says to find all the intercepts of the following equation. Me telling you the answer is pretty much the only way to go through the problem, go through the worked out solution. So I'm not going to actually tell you the answer. The only hint I will give you for this problem is that the form that this is currently written in is called intercept form. So that's my hint to you on what the intercepts would be. So go ahead and look at the answer choices that pop up right now and select the correct answer for the intercepts of number 22. All right, so now that you had some time to think about it, the intercepts for this, since it is in intercept form, the intercept that comes from this factor, remember that as a factor we have x plus 3, but when we want to go to the intercept form, it would be x equals negative 3. So the x-intercept would be negative 3, comma 0 for that factor. For the next one, we have x minus 7. Well, as a factor, it's x minus 7. As an intercept, we would call that 7, comma 0. And last but not least, notice that it does not state only the x-intercepts. We also have to include the y-intercept. So the y-intercept would be plugging in 0 for x. If we plug in 0 for x, let's see what we get. This would be negative 0 plus 3 times 0 minus 7. So that's negative 3 times negative 7, which happens to be positive 21. So our y-intercept is at 0, comma 21. Hopefully you chose that as the correct answer. Number 23 says to find the vertex of the following equation. Again, I'm not going to tell you what the vertex is. I will just tell you that this is in vertex form. So think about the vertex of a quadratic expression and select which of these is the vertex. All right, so since this is in vertex form, the vertex is the same thing as the locator point for a quadratic expression, and the locator point comes from h comma k. So the locator point is at negative 3, because remember that it was x minus h. So if I wrote that, it would be x minus a negative 3. The double negative turned back into a positive in the equation. So h is negative 3, and then k is plus 8. So negative 3, comma 8 is the answer you should have chosen for number 23. All right, number 24 and 25. We're going to do number 24 together, and I want you guys to do number 25 on your own. So for number 24, this is a composition, coming back to that function machine from earlier. This means to take 2, substitute it into g, get an answer for g, and substitute it into h. So we're going to take 2, substitute it into g of x. And we're going to get an answer from that. So let's come over here to our table. Here's x equals 2, and I know that because in this first row, these are all the x values. So this first one is x equals 1, x equals 2, x equals 3. So we have x equals 2. If I want to substitute 2 into g of x, I need to find the row that is labeled g of x. So here it is. If I substitute 2 into the function g of x, this is telling me that the answer I'm going to get is 1. So when x is equal to 2, g of x is equal to 1. So substituting 2 into g of x gives me 1. Now, that's an intermediate answer. That is not my final answer. So all we did was take 2 and substitute it into g. We need to take the answer from that and substitute it into h. So now let's substitute that into h of x. When I substitute 1, so let me erase this. Oops. When I find x equals 1 and substitute that into h of x, come down to this third row, it tells me the answer is 3. So when x is equal to 1, h of x is equal to 3. So my final answer is 3. I want you guys to try that for number 25 and go ahead and answer number 25 now. All right, for number 25, we're going to take 3 and plug it into h of x. When we get an answer for that, we're going to take that answer and plug it into g of x. Our final answer will come out of the result of g of x. So if we come back up here to our table, taking 3 and substituting it into h of x gives me, when x is equal to 3, h of x is equal to 2. So my intermediate value is 2. I'm going to take 2 and substitute it into g of x. So when x is equal to 2, g of x is equal to 1. So my final answer is 1. Hopefully that's what you entered. Number 26 and 27. We are going to do number 20. Which one are we going to do together? We're going to do 27 together, and you guys are going to do 26 on your own. For number 27, this is the exact same type of problem from before, but this time we're doing it from a graph. So for number 27, this means to take 3 and substitute it into f. I'm going to get an answer. We're going to take that answer and substitute it into g. So 3 into f of x. Take the answer for that and substitute it into g of x. And whatever I get out of g of x will be my final answer. So taking 3 and substituting it into f, let's see what we get. Let's find 3, because remember 3 is an x value, so let's find 3 on the x-axis. Here's x equals 1, x equals 2, x equals 3. Now, I want to substitute this into the function f. So f is this straight line. So I want to find out where x equals 3 intersects this line right here at f. So if I put a point there, this is the point. Three, comma, 1.5. It's a decimal, that's why we're doing this one together. So when I plug in 3 to f, I get out a y value of 1.5. So my answer to this first part is 1.5. That's my intermediate value, 1.5. Now, let's take our intermediate value of 1.5 and substitute it into the function g and see what we get out as our final answer. So let's find 1.5 on the x-axis, because now this is an x value. So here's x equals 1, here's x equals 2, x equals 1.5 would be right in between them. And we're going to substitute that into the function g of x. So 1.5 for an x value, I'm going to go up until I hit the function g of x, which is this parabola. And this is the point right here that I've attained. So I'm going to put a point there. And this is the point, 1.5, comma, 4.5. So that tells me when I substituted 1.5 into the function g, I got out, my output was 4.5. That means my final answer is 4.5. All right, I want you guys to try number 26. So go ahead and try that one now and put your answer in when you get it. Okay. For number 26, this means to take 1, substitute it into g of x. When you get an answer for that, your intermediate answer, you're going to substitute it into f of x. And your final answer will be the result of whatever comes out of f of x. So if we substitute 1 into g, Here's 1, go up to g, and you get 4. This is the point 1 comma 4. So my intermediate value is 4. Take 4, substitute into f of x. So come over here to the x-axis again. Here's x equals 1, x equals 2, x equals 3, x equals 4. And then go ahead and follow it up. Here's where that intersects the function f, where 4 intersects f, and this is a y value of 2. This is the point 4 comma 2. So my final answer is 2. Hopefully you guys put that. The next ones we're going to talk about are about functions. So hopefully you guys remember our function vending machine example. This is a function, and this is a relation. Sorry, I don't know where my Mountain Dew went. There's supposed to be a Mountain Dew picture there. Anyways, this is a function because when I push 1, I know I'm getting water. When I push 2, I know I'm getting chocolate. When I push 3, I knew I was getting a Mountain Dew, so on and so forth. This was not a relation. It's kind of anticlimactic without our Mountain Dew there. Mountain Dew. There we go. This is not a function, it's just a relation because when I push 3 in my vending machine, I might get a Mountain Dew or I might get a Pepsi, and that's not okay. We can't have an uncertainty about what we're going to get from our functions. So if we have x values, if we have domain values going to more than one range value, that's a problem. Remember, we also had that inefficient vending machine where you could push any number and you would only get water. And we said that's still a function. It's just kind of an inefficient function. Why would you need that? But it is a function because I know exactly what I'm going to get no matter what button I push. So with that said, let's look at number 28 together. When I push 0 in my machine, I know I'm going to get 7. When I push 2, I know I'm going to get 10. When I push 4, I'm going to get 5. 6 gives me 0. 7 gives me 0. And 8 gives me 3. Notice that of these times, none of them repeat. I know exactly what I'm going to get for every single time. Now, some of our y values repeat. Notice that 0 got repeated twice, but that's okay. If I push 6, I know I'm going to get 0. If I push 7, I know I'm going to get 0. Perhaps a little inefficient, but that's okay. This does represent a function. So for number 28, I'm going to say yes, this is a function because none of the x values repeat. All right, I want you guys to try number 29. Tell me whether or not that's a function and explain why or why not. All right, now that you've had some time to think about it, hopefully you wrote something along the lines of, no, this is not a function. And the reason it's not is because of these two coordinate points right here. We have 4 going to 1 and we have 4 going to 0. That is a problem for us. This is not a function. I'm not sure what I'm going to get if I push 4 in my function vending machine. So this is not a function because we have x values repeating. All right, domain and range. Let's look at number 30. Now, domain is x values. It's all of our x values. Range is all of our y values. So when I do domain problems, I like to kind of highlight the furthest point to the left and the furthest point to the right. So I've highlighted here in yellow the furthest point to the left and the furthest point to the right. You've seen that there are no other points on the left-hand side of this, and there are no other points on the right-hand side of this. So let's look at x values. This is an x value of -5. Notice this is an open circle. So when I write my domain, I'm going to say that my domain is from -5, and it's a parenthesis since it's an open circle, all the way over to the furthest point on the right, which is +5. And that's going to be a bracket because we have a closed circle over here at +5. For the range, I'll highlight it in orange. Range is all of the y values. We go from the furthest point to the bottom, that's the lowest point on the graph, all the way to the highest point on the graph. So the lowest point on the graph is down here. Notice there's an open circle here, but we have some closed circles over here. So we can go ahead and put a bracket for range, and our lowest y value is at -2. So our range is going to go from -2 all the way up to our highest point on the graph, and this is our highest point on the graph. Notice that it's a solid line that indicates that those are closed circles. We're going to put a bracket at +2. All right, for number 31, I want you guys to try that one on your own. Go ahead and think about it and select the correct answer. Okay, for the furthest point to the left, This one's a little funky because some of the points are pretty close, so be careful when you do this. The furthest point to the left is over here at -4. The furthest point to the right is right here at 3. This is a closed circle, so it's a bracket. This is an open circle, so it's a parenthesis. Therefore, for domain, we have -4 to +3. For range, our lowest point on the graph all the way up to our highest point on the graph. Our lowest point on the graph is an open circle down here at -5. Our highest point on the graph is also an open circle up here at 5. Our range, therefore, is from, with parentheses since it's open circles, -5 at the bottom, all the way up to +5 at the top. And that's your domain and range. All right, the next one I want to look at, we're almost done. You guys have been doing great. The one I want to look at next is 32. I'm not going to necessarily tell you guys how to do this one, but I will give you a hint. Remember that when we have f of x minus g of x equals 0, my hint to you is I want you to remember that f of x minus g of x equaling 0 is the same thing if I add g of x over to the right-hand side, because as long as you do it to one side, you can do it to the other. We're balancing the equation. On the left-hand side over here, negative and positive g of x would add to 0, and that would leave us with f of x equals, on the right-hand side, g of x. Now, that's as far as I'm going to tell you. I'm not going to tell you any more about this problem. I want you guys to go ahead and try it on your own, but that's just my little hint to you. All right, let's look at 33. For number 33, it says, using the graph below, determine the average rate of change in baseball salaries between 1991 and 1994. Notice I've put our little average rate of change formula over here. So from 1991 to 1994, let's go ahead and find those points on the graph. Here's 1991. I'm going to go ahead and follow it up, and I'm going to put that point right there. So 1991, boom. If I had to estimate that point, I would say it's 1991, comma, and then probably about, let's just round. I'm going to say 0.9. This is supposed to be a rough approximation, 0.9. For the other one, 1994, follow that point up right about here. I'm going to say that's 1994, comma, it's pretty close to 1.2, so I'm going to just say 1.2. Now, this one was a little lower, but this one was also a little lower, so it's probably going to be pretty accurate, actually, to what it's supposed to be. So we have our y2s and our y1s. We have our x2 and our x1. Let's go ahead and plug them into the average rate of change formula. So y2 minus y1 over x2 minus x1. Now remember, you get to use a calculator on the test, so if you need to go ahead and pull out a calculator now, please do so. 1.2 minus 0.9. Let's go ahead and put that into our calculators. 1.2 minus 0.9. I'm getting 0.3. On the bottom, 1994 minus 1991 is 3 years. So that's 3. So in our calculator, 0.3 divided by 3 gives us 0.1. Now, remember that we have to have meaning. The purpose of average rate of change is that it has meaning. So we are trying to find the average rate of change in baseball salaries. So let's look at the units. The units on the y-axis are salary in millions of dollars, and then the units on the x-axis are years. So we are going to say that the rate of change in baseball salaries is $0.1 million per year. Perfect. Now, $0.1 million might not have a lot of meaning to you. So if you think about what 0.1 of a million is, it's 100,000. That means that the rate of change in baseball salaries is $100,000 per year between 1991 and 1994. That's the average rate that people's salaries were changing in those years. All right, I want you guys to try number 34. Oops, too far. Oh, I didn't even put it on here. I want you guys to try number 34 on your own, and then you guys can check your work on the answer key. Let's look at 35 together. So we're going to do B together, and then you guys are going to do A on your own. Down here at the bottom, I put the general equation of what this should look like if we have A, H, and K. So this black function is our original function. you guys need to write the equation for A, and we're going to do B together, and then later you guys can go back and look at C on your own. So for B, let's look at B together. I'm going to choose a point that started on the x-axis. I'm going to choose this point right here. Kind of helpful if it starts at 0, 0. I want you to locate that point on the new graph. So here it is on the new graph. Notice that to get from this original point to this new point, we didn't have to move up or down. We just had to move all the way to the right. That means there is no k value. It did not shift up or down. There is no k value. It did shift to the right, however, so there is an h value. Our h value happens to be 6. So for B, so far we have y equals, now there actually is an a value, so I'm going to leave that a part off. F of x minus 6, and there's no k value, so I'm not going to put a k. So to find a, it kind of helps if you just kind of do some counting. So choose 2 points. I've chosen 1 point here. I'm going to choose another point on the graph. I'm going to choose this point right here, and I'm going to label its corresponding point on that new graph. So notice that to get from this purple point to this purple point on the original function, if I count, I'm counting over 1, 2, 3, 4, 5, 6, and then up 1, 2. Now count over that same number of units on this green one, over 1, 2, 3, 4, 5, 6, but this time notice if there's a difference in how many you count up or down. So from here, I'm only counting up 1 unit this time instead of up 2 units like I did before. So since I'm only counting up 1 unit, that's half of what I was counting up before, which means my a value is half. It's compressed by 1/2. So I want you guys to try and find the equation for a now. So go back and choose which answer you think a would be. All right, let's talk about a together really quick. Notice that the shape of the graph is the same. Here, to get from this point to this point, we counted over 6 and up 2. On this red graph, it's the same actually, over 1, 2, 3, 4, 5, 6, and then up 1, 2. So the shape is the same. It has not been reflected or compressed or stretched. The shifts, however, remember how we said to kind of locate some points on the graph and see where they are now? So if this point at 0, 0 on the original function has moved over here on this new graph of a, that means it moved 3 units to the left and 2 units up. So my h value is -3 and my k value is +2. So when you chose the graph, hopefully you chose the one that said f of x plus 3 because of that double negative, x minus a -3, and then +2 on the outside. All right, make sure you try C before you finish your worksheet, but the last one we're going to look at together is number 36. For number 36, given the solid function below, graph the transformations. We are going to look at C together, and then I'm going to have you guys try A on your own. So for part C, we have a couple things happening. We have a negative, that's a reflection, and then we have +6 that's inside of the function. So remember, anytime we have a number inside of the function, that is going to be a shift to the left or right. This one happens to be the left because it's +6. That means we have that double negative. So the first thing I'm going to do is I'm going to show the reflection. I'll do it in green. So all these points just get reflected up above. So from -2, we have this point at -3, -2. It's now going to be at -3, +2. So I'm going to put this little ghost point on the graph. We have this point at -1, -2. Now it's going to be at -1, +2. We have this point at 1, +2. Now it's going to be at 1, -2. And then we have the point at 2, +2. It'll be at 2, -2, like this. So there's the reflection of the graph. Now, I don't actually want these points connected. I just wanted to show you what they look like once they're reflected. All we've done so far is that negative piece right there. We still have to shift all the points left 6 units. So I'm actually going to erase this. And now in red, I'm going to plot these final ones. So this one, if I shift it left 6 units, it's going to go all the way over here to -9. If I move this point to the left 6 units, it's going to go all the way over here to -7. If I move this point to the left 6 units, it's going to go all the way over here to -5. And if I move this point to the left 6 units, it's going to go all the way over here to -4. So now I can connect these points And that is the answer for C. So go ahead and jot that one down. Now, I'm going to have you guys do A. I'm going to have you guys graph the transformation for A. And in order to check to make sure that you know how to do it right, I'm going to ask you a question. The question I'm going to ask you is, I want to know where this point ends up. So when you move this around, left and right, up and down, reflect, stretch, all that good stuff, when you move this point around, with this function, f of x minus 4 plus 1, where does it end up? So go ahead and graph it, think about that for a minute, and select the correct answer choice. All right, now that you've had some time to think about it, f of x minus 4 means we're shifting to the right 4 units, and then the plus 1 means we shift up 1 unit. So from here, if we're shifting right 4, 1, 2, 3, 4, and then up 1, it ends up at 6, 3. 6, 3. And then the rest of the graph kind of just follows suit. Hopefully you have something along the lines of, I mean, mine's not perfect, but it looks something like that. As long as it's up there in the region, I'm sure you have your points correct. I didn't make it very accurate on mine. All right, that's the end of this video. Make sure to complete the rest of the problems that we didn't get a chance to do together.